Welcome back. In this video, we'll continue discussing the inelastic scattering inside TEM. In the previous videos, you have learned that scattering can be elastic or inelastic. When the scattering is inelastic, you can generate information such as characteristic X-ray and cathodoluminescence. In this video, we'll look at other signals such as Auger electrons, plasmons, and phonons as a result from inelastic scattering. We'll also extend our knowledge to beam damage in TEM. The high-energy incident electron can knock out a core shell electron, leaving behind a hole. The configuration is not stable, so the electron at a higher energy level in the material will fill in the hole. Then there is excess energy to be released. Until this part, the process is similar to that of the characteristic X-ray generation. However, in the low atomic number elements, the energy is released more likely in the format of Auger electrons than the characteristic X-ray. That's why in the low Z materials, we do not have a lot of X-ray emission. That's one of the reasons why EDS should not be used to quantify light elements. The inelastic scattering can also lead to the generation of plasmon and phonon. Plasmon can be viewed as the collective oscillation of electrons in the material, and the phonon can be viewed as the collective oscillation of atoms in the material. You can capture the plasmon and the phonon information using the electron energy loss spectroscopy EELS in TEM. To get the plasmon information is relatively easy. To obtain the phonon information is challenging. Professor Phil Batten at Rutgers University is an expert in this area. We will learn more about plasmon and phonon when we talk about the EELS part of this course. Beam damage in TEM can be also associated with inelastic scattering, and it is usually termed as the knock-on damage. Knock-on damage severs the bonds in your specimen and can create point defects as well as trigger phase transformation. The example on the left is from my student De Xing, and the material is a magnesium alloy. By exposing a small part of the material under the beam, you can see the generation of point defects, which later turned into dislocation loops and vacancy clusters. The work on the right was done by Chu and Deng. The sample is silicon. By converging the beam, you can actually drill a hole in the specimen. By exposing the specimen under the electron beam, you can turn the crystalline silicon into amorphous. When looking at polymers inside TEM, the beam damage can be more pronounced. In this example here, the specimen is melting. Again, this is a result from beam damage due to the inelastic scattering. I think it's just something really fun to watch inside TEM. Another thing that is worth mentioning here, but not really a result from the inelastic scattering, is the carbon contamination. Because inside TEM the vacuum is not perfect, so by dwelling the beam at the same spot for a long time, you can see those carbon contamination on the specimen surface. By now, I hope you have established a good understanding of the electron beam material interaction regarding scattering. Starting from the next video, we'll shift gears a little bit and talk about the TEM instrumentation.